make sure, please pay attention, make sure you understand the operating principle of BJT. If you do not know the operating principle, how to operate your machine, then you don't understand, then it's going to be hard to make use of this transistor to solve another application. So make sure you guys understand the operating principle, how it works. Just to reiterate, we have transistor symbol like this. This is the collector terminal, this is the emitter terminal, and this is the base terminal. And we said that this is NPN transistor, NPN transistor. That's the transistor that we are focusing on. So this PN, which means P-type material, will be in the base. So this is the construction mechanism. So here you have the base, here you have P-type material, here you have N-type material, and here you have N-type material. So now, you see PN, you can think of this as a diode. PN, this junction, you can think of this as a diode. And you can think of another diode right here. PN. So our diode symbol is like this. So this is the P terminal, this is N terminal, another one, this is anode terminal, this is cathode terminal. So you can think of this P and a base and emitter terminal, you can think of this as a diode. And PN, you can think of this junction as another diode. Okay? So that way it's easy to visualize that. Now, when I say in saturation mode, what you have, the base emitter junction is going to be forward biased. Base emitter junction is going to be forward biased, just like in active mode, base emitter junction forward biased. Saturation mode, base emitter junction is forward biased as well. And I'm going to tell you what is saturation mode in a moment. And base collectors or collector base junction is going to be forward biased as well. But in active mode, when your transistor is going to operate as an amplifier, then your collector base junction is going to be reverse biased. Okay? So there was a question about the active mode in your exam. But in saturation mode, both collector base junction is going to be forward biased and base emitter junction is going to be forward biased as well. Now, what does that mean, this forward bias? Forward bias means that the voltage at this terminal, voltage of this terminal is going to be, let's call this VB, and voltage of this terminal, let's call this VB, with respect to ground, and this voltage with respect to ground, which means that base emitter junction forward bias means VB is greater than VC. Base emitter junction is forward bias means VB greater than VB. Similarly, base collector junction forward bias means, let's call this voltage. Let's call this voltage VC with respect to ground. Now, to make base collector junction forward bias, what do we have to do? What is the condition? Base collector junction has to be forward biased. Yes?
Would be VB greater than VC?
Exactly. But in active mode, this is okay for active mode, but this is going to be reversed for active mode. But in saturation mode, this is going to be condition. VB greater than VC. So which means this diode has to be forward biased. These both junctions will be forward biased. Now, look, now this transistor, I have just redrawn this transistor just to match it with the board. So this base terminal is right here. This emitter terminal is this emitter terminal here. And then this collector terminal is right here. Now, base emitter, this base emitter junction, you can think of this as a diode. See, there is a diode right here, and I'm naming this diode D. And base collector, you can think of this as a diode. So you see that there is a diode right here. And current flowing through this diode, I denoted with IBC. And remember the convention, guys, BC, which means that the base to collector. BC, IBC, current flowing from base to collector. So this diode is going to be forward biased. Now the current that is coming through this collector terminal, I denoted with IC, and this is the IC that we are talking about. Okay? This is the IC that we are talking about, this collector current. Now, the overall collector current that will flow from collector to emitter is going to be denoted as such. Okay. Now, if you apply KCL, don't you think that this current plus this current equals this current, right? Using KCL, this current plus this current is going to be this current. So IBC plus IC equals this, and you must have a current flowing from IB. Okay. Now, if you see the Shockley equations that we went through, the collector current, this collector current is going to be this overall current using Shockley equation minus the current flowing through this diode. So minus the scale current due to the base collector junction forward bias. So this is IBC into the VBC over VT. So this current is basically right here. So you are subtracting this current, you are subtracting current flowing through this diode base to collector from this overall current to get the collector current, and this is basically what it is. So basically, just KCL. You are applying KCL at this node, and these are just Shockley equations. So make sure you go through this exercise, guys. 2 exercises from the textbook. Include them in the scribing. I think this is the last scribing. Make sure you include this in your scribing. Now, in saturation mode, which means that the collector voltage is going to be less than the base voltage. As long as this condition is true, then you are in saturation mode. But in active mode, VCB, which means VCB equals VC minus VB. VCB, this voltage is going to be opposite of VBC. So VBC equals negative VCB. Now this VCB, as long as VCB is positive and up to certain negative voltage, that's okay. The transistor is going to be operating in active mode. But when VCB becomes more negative, which means means this voltage is less than this voltage, then this becomes positive, this becomes forward bias, then you enter into saturation mode. In saturation mode, your collector current, you are reducing the collector current. In saturation mode, you are reducing the collector current. As you can see, at some, when VCB reaches certain negative voltage, so saturation IC current flowing through the collector is reducing drastically, and that's the point where you experience saturation mode. And active mode, just to reiterate, active mode is very important because in most cases you will see BJT will be operating BJT in active mode. When we use this BJT as an amplifier, okay? In saturation mode, we use this BJT as a switch, like power, either turn on the, either make this transistor look like a piece of wire, or make this transistor just like an open circuit, okay? In saturation mode, we use transistor as, I have written this in my slide, as switch. And in active mode, we use this BJT as an amplifier. Okay. The base current, just so that you know, this base current is going to be low. This collector current in active mode, this collector current is going to be beta IB. Okay. Now, here the scale current that you see for this diode, base to emitter, the scale current you will see, this scale current is going to be divided by beta, given the transistor's gain. This is the gain, DC gain of the transistor. So the scale current for the base emitter diode is going to be IS over beta. So 100 times less than. So it will just scale down the scale current for base emitter diode by beta. So that is the reason that you see. So this is basically your IC collector current. You are basically scaled down the collector current as such, plus IBC, whatever current going from base to collector. So as you can see, IB is IC over beta plus small current. But in active mode, this part was zero, because in active mode, base collector junction was reverse biased. In active mode, base collector junction was reverse biased. So this part was zero in active mode. But in saturation mode, because the base collector junction is forward biased, so you do see some current. Now in saturation mode, VCE, usually VCE, the voltage between collector and emitter terminal. So this is the transistor. This is base, this is collector, this is emitter. This voltage is basically your VC. This voltage is basically your VC. This voltage in saturation mode approximately 0.2 volt, which is close to 0 volt. So you can just think of this as a piece of wire. So when transistor operates in saturation, which means that you can just think of this as a piece of wire. Ideally, you can think of this as a piece of wire. But practically, you see this voltage between collector and emitter is about in the range of 0.1 to 0.3. And you'll see that you can take a voltmeter and you can measure the voltage. You will see that it is approximately 0 volts. But this is the range, depending on what type of transistor you use, this is the range that you will see. So when transistor operates, when transistor is on, which means that the transistor acts like a switch, closed switch, which means that VC is going to be approximately 0.2 volt. All right. So that's all the theory, and this is the PNP transistor, construction of a PNP transistor, which is just the opposite of NPN. Now we will move on to IV characteristics. IV, current voltage characteristics. IV characteristics. So this IV characteristics we start with applying DC voltages. So we apply for NPN transistor, this is PNP transistor. So P and P, and this is NPN. N, P, N. So we apply certain voltage between collector and base. So we call this VCB, and this is DC voltage. Okay. And we apply another DC voltage here, VB2. These are DC voltage as well. EB junction, emitter base junction is forward biased, which means that this voltage has to be more than this voltage. In other words, VBE, just to remind you guys, VBE, this is where you get confused. I'm just going to explain one more time. Very, very basic. Okay. Again, a simple electrical element here, and it has two terminals. We have, let's say, one terminal polarity I mentioned as such, positive, negative, and this is terminal A, this is terminal B. It's a two-terminal device. When I say voltage VA, voltage of this terminal VA means that you take a voltmeter and you take a voltmeter and you measure the voltage of this terminal with respect to ground. This is your VA. And VB is the voltage when you take a voltmeter. When you take a voltmeter, V with respect to ground. With respect to ground, you see this voltage is the B. And the voltage between A and B we denoted with VA. And this VAB is basically whatever voltage you get with respect to ground at terminal A minus whatever voltage you get with whatever voltage you get of terminal B with respect to ground. So that's the convention. That's how the convention works. And I'm going to use this concept, class. I'm going to use this concept in the coming example. So when I say VBE, which means that the voltage between these two terminals, if you measure voltage between those two terminals, is going to be VB. Similarly, voltage between those two terminals is going to be, depending on how you polarize, if this is positive, this is negative, it is going to be BC. Or if this is positive, if this is negative, it is going to be BC. Is that clear, guys? Hmm? Just depending on the polarity, you denote, you have different notation.
Yeah, what's the symbol that connecting the two, like the C and the IB node? What's that symbol?
This symbol?
Yeah.
Oh, this symbol is called voltmeter.
Oh.
This
okay.
symbol V is voltmeter. Voltmeter. And you use this symbol, it is ammeter. Okay. And we use this symbol to denote power meter. That's the standard convention. And you guys are using multimeter, right? Multimeter, that you can use that multimeter as a voltmeter. You can use ammeter. You can use ammeter, and you can use it as a what is the ohmmeter?
Oh.
Yeah. To measure resistance, so ohmmeter, ammeter, voltmeter all together. That's why you call it multimeter. Okay. So we are going to run IV characteristics of this transistor, NPN transistor. Let's move on. Before I go through the example, just to summarize all the equations, because we need these equations. And you already know this equation. IC equals IS into the VBE over VT. This equation is the first part of your laboratory experiment number 4. It's IC and VBE characteristics. IC versus, it's not minus, guys. VBE, which means that IC is a function of VBE. VBE. Okay. Do you see that it's an exponential term? IS is constant and VT is constant, and it depends on VBE. It's an exponential curve, right? So you should expect curve like this. So if this is IC and this is VBE, you should expect a curve like this. IB, the base current, is going to be IC over beta if it operates in active mode. In other words, IC, substitute the expression for IC right here, IS over beta into the VBE over VT, the VT. So you see that this is the equation for IB, and IE is going to be IC over alpha, and alpha is about 0.98 to 0.99. 97 to 0.99. IC and IE, there, as you can see, almost all the collector current goes to the ammeter, but because of small base current, you see this alpha is close to 1, but not exactly 1. And IC equals beta IB. So I have just summarized all these equations. And the relation between IB and IE, as you can see here, IB equals IE over beta plus 1. And IE is beta plus 1 times IB. Beta equals alpha over 1 minus alpha. And alpha equals beta over beta plus 1. And Vt is Boltzmann constant times the temperature, the room temperature divided by the charge of an electron, which is 25, approximately 25. So the other term that you will see in the data sheet is called collector base reverse current. This current you will see when emitter is open. When emitter is open. So when emitter is open and collector base junction is reverse bias, you will still see a small current from collector to base. Very, very small current when emitter is open. Okay, emitter is not connected to anything. So you will see a small current flows from collector to base. C, B, collector to base. I, current flowing from collector to base when emitter is open. So that current is called, ideally there should not be any current, and because of the construction mechanism, a small, very, very small leakage current flows from collector to base when it is reverse bias. Okay, so that is the terminology that you need to know. Let's go through this example. So in this example, the transistor in the circuit below has beta equals 100. What is this beta? Beta equals 100. What does that mean? Immediately you can say that the collector current is going to be 100 times more than the base current, right? IC equals beta IB. So immediately you can say that the collector current is going to be 100 times more than. So this collector current, IC is going to be 100 IB, which means that the base current, if you use base current, you get a base current as such. Okay. Now, exhibits a VBE of 0.7 volt at IC equals 1 milliamp. So VBE when IC is 1 milliampere, guys. When IC is 1 milliampere, the VBE is 0.7 volt. And design the circuit so that the current, we want this current to be 2 milliamp. We want this collector current to be 2 milliampere through the collector, and a voltage of 5 volt appears at the collector, which means that the voltage of 5 volts. So VC is 5 volt. VC is 5 volt appears at the collector. When you say design the circuit, what it means, you just need to know what is this collector resistor, how much is this collector resistor, and how much is this emitter resistor. Given these voltages, again, you can think of this as positive. I'm going to use direct battery DC. So this is your and this is VCC equals 15 volt with respect to ground. Okay, guys, it's better because there is a ground here already. You can just put it the other way. So here, there is a ground. So this is 15 volt. and we call this VCC. VCC. And we have VEE is negative 15 volt. Negative 15 volt means that look, this is positive, this is negative. If positive, you connect it to ground, and negative, you connect it right here. And this is your VE. So which means that your voltage of this point, the red lead, voltage of this point, you have voltmeter, red lead, this is positive, and your black lead is right here. Is going to be negative 15. So this negative 15 volt means that the voltage of this point with respect to ground is going to be 15, negative 15, where the battery is connected as such. Just going to remove this, just for clarity. Okay, guys, we have all the parameters. Now I'm going to write the solution. Yes.
Could you find RC by using Ohm's law, like divide by
Exactly.
voltage? Okay.
Exactly. Immediately, we know how much current we are supposed to get. 2 milliampere, and we know this voltage. Okay. Immediately we can find what is RC. Immediately we can find RC. Clearly, RC equals VCC minus VC over IC, which is 15 minus 5 over IC. We want 2 milliampere, right? 2 times 10 to the negative 3. How much is it? 10 over
5 times 10 to the third, so 5 kilowatts.
5 kilo. Okay. One answer we found immediately. Okay. And what else? We need to know what is RP, right? But to know what is RE, we need to know what is this voltage. This is positive. Please pay attention, guys. This is positive, this is negative. So this voltage this is negative, this is positive, and this is your VB. VBE, let's call this VBE2, that we do not know, but what we do know that VBE is 0.7 at IC equals to 1 milliampere. What is our requirement? Our requirement is IC equals 2 milliampere, right? Our requirement is design a circuit so that the current 2 milliampere flows through this current. So our requirement is 2 milliampere. And at 1 milliampere, it is known that VBE is 0.7. So when let collector current IC1 equals 1 milliampere when VBE 1 equals 0.7 volt. And collector current IC2 equals 2 milliampere when you have base emitter voltage VE2 equals what? We do not know. We do not know what is the voltage when more current flows through the collector. So we can just use IC versus VBE characteristic equation, which is IC1 equals IS times Shockley equation. Using Shockley equation, IS e to the VBE 1 over VT and let's give this equation number 1. And IC2 is IS e to the VBE 2 over VT.
So you said IS instead of IC.
IS, yes.
Yeah.
Now we have these two equations. If we dividing, okay, 1 or dividing equation number 2 by 1 gives IC2 over IC1 equals what? IS disappeared. So you are left with e to the this guy divided by e to the this guy. So these are power, therefore you can write e to the VBE 2 minus VBE 1 over VT. So let's call this e to the let's keep it like that. Now your VBE 2 minus VBE calculator, guys, and your calculator. If you take natural logarithm, so if you get natural logarithm of this part, so natural logarithm of IC2 over IC1 and you multiply with VT. It is going to be VBE 2 is going to be VBE 1 plus VT natural logarithm of IC2 over IC1, which is going to be 0.7 plus 25 times 10 to the negative 3 natural logarithm of 2 over 1. 2 milliampere over 1 milliampere. So natural logarithm of 2. So how much is it, guys? VBE 2 equals 0.7 plus 25 e negative 3 times log. It is 0.717. 717. 0.717. So this is your VBE2. So we did find VBE2 when IC is 2 milliampere. Now look. So again, this is your transistor. We found RC. So this is VCC equals 15 volt. and we found IC, we are given IC, we want IC to go on median here. And here is RE. And this is your, actually, this is VEE equals 15 volt with respect to ground, and this is connected to ground, guys. This is positive, this is negative. Now we have this VBE, these voltage, we have VBE, we found that, okay? Now, what is this voltage?
0.717.
VE. VE with respect to ground.
Isn't it the same thing as VBE too?
No, VBE is voltage of this point with respect to this point. But this voltage is voltage of this point with respect to ground. So this point, this voltage, again VBE is this voltage minus this voltage is VBE. But this voltage is 0 volt, it's connected to ground. So VE, okay, use you scale here, guys. Okay, so you have positive, so this is ground. VBE is, this is negative, this is positive. So VBE 2 is 0.717, which is same as negative VEB 2. So what we are going to have, this voltage VE is exactly same as negative VE2, which is negative 0.7171. So this voltage with respect to ground is going to be 0.717. Now, the drop across RE, the voltage drop, that's the voltage drop RE, VRE. The drop across RE is going to be VRE is going to be VE minus 15, which is minus 0.717 plus 15, which is 5.717. Oh no, sorry. It's 14 point. How much is it, guys? 15 minus, is it? 14.283 volt.
Yeah.
So that's the voltage across RB. Now we found this voltage. If we know what is the current, so current is I sub E. Do you guys remember that I sub E is simply IC plus IB, which is basically IC times 1 plus 1 over beta. IB is IC over beta. So we know what is IC, which is 2 times 10 to the negative 3, 1 plus 1 over 100. So this you will see is 2.02 milliampere. So your IE is 2.02 milliampere. If I sub E is 0.02 milliampere, therefore R sub E is voltage across resistor RE over I sub E is going to be 40.283 over I sub E is 2.02 times 10 to the negative 3. So this is going to be 7.07 kilo. So R sub E is 7.07 kilo. Now we are going to design the circuit. So our complete circuit is as follows. So this was 15 volt. RC equals how much? 5 kilo. IC would be 2 milliampere. And RE is going to be 7.07 kilo. And this is going to be negative 15 volt. And the base is going to be connected to ground. Yeah, that is the complete circuit. That way we know all the parameters. We know RC, we know RE, we know the current. We want current IC flowing through the current terminal. We know IB. We know IE. IE is going to be 2.02 milliampere. As you can see, it is almost IC, but because of small base current that is flowing, because this voltage is negative compared to the base. You see that? This voltage is negative compared to ground. So you will see a small base current flowing. So that is the reason it is 0.02. So the base current is going to be 0.02 milliampere. So base current is 0.02 milliampere. Okay, 0.02 milliampere, what does that mean in terms of microampere? It's 20. Right?
Yeah.
20 microampere. The base current is going to be in the range of microampere, and the collector or ammeter current is going to be milliampere. Do you see? How much DC current gain that you see? So that is the reason you use BJT when you need high current gain. So this is one example. For IC versus VBE characteristics. Now we see another type of characteristics, common emitter IB characteristics in active mode. In active mode, I'm not going to go through the theory, we went through it many times. In active mode, you apply this voltage, VCE, voltage between collector and emitter. You vary this voltage and you vary, this is exactly what you'll be doing in the lab guys. This is exactly what you'll be doing. You vary VCE, this is the primary sweep and this is the secondary sweep. This is primary sweep, this is the secondary sweep. You vary VCE and you vary VBE, you get, for different VBE, you get curve like this. Now, as you can see here, you see it's kind of, it's not like that. It's not like that. There is an angle here. There is a reason. Okay, this is called early effect. That this collector current varies still when it is in active mode. Collector current is going to vary kind of linearly, not exactly linear, but very small, kind of resistive response. So if you extend this, they will at some point meet at point, and that point is called early effect voltage, V sub A. And this V sub A is the voltage for early effect. Ideally, this V sub A, this voltage due to early effect, that, you know, the collector current is not flat when it is active mode. It is slanted, there is a bit of slope right here, it is a bit slanted. So, it's because of the early effect. There is a small resistance between collector and emitter. There is a very, very small resistance. And because of that, there is a resistance. I should not say small, you will see how much is the resistance. But because of that, because of this resistance, output resistance, VA over IC, you see this curve should have a bit of slope right here. Almost zero. Slope is almost zero. Ideally, the slope is zero, but practically you see some slope because of the early effect. So early effect, what does that mean? That the collector current increases slightly with VCE due to finite base width modulation effect. And this is the equation. And if V sub A is infinity, this term becomes zero, and IC would become flat like this. Okay? So this is the equation that you will be using in case you plan on doing MATLAB portion of the FEELAB. And then you have, I use, to draw this plot, I use these parameters. So scale current I used 10 to the 15 ampere, VT 26 milliampere, V sub A 50 volt. Now, the large signal equivalent model for circuit in active mode with output resistance. Output resistance is going to be between collector and emitter, as you can see. This RO is going to be V sub A over IC. And this is the DC current gain, and the scale current for the base emitter junction diode is going to be IS over beta that we went to. And we have this voltage between VB as such, which means voltage of this point minus voltage of this point is your VBE. So, in saturation mode, I actually zoomed in this part. And I drew the plot again right here. So that's how you see the saturation region. So this is the active region, this is the saturation region. In saturation region, your collector current is going to be reducing by this much. And VCB is VCE minus VBE. If you substitute, you can actually bring this part out. And this exponential curve is coming due to this one. This expression models nonlinear behavior of IC, and it is due to this part of this equation. So we went through this equation. I just manipulated this equation right here. But in the laboratory, all what I want you to do, you just plot active modes with different VB. So we'll have primary sweep VCE and secondary sweep VBE. So on Thursday, please bring your laptop, or we'll be using our laboratory to make sure you understand the primary sweep and secondary sweep. Primary sweep is going to be VCE, secondary sweep is going to be VBE. So we will be drawing these characteristics curve for transistor that we have in the laboratory. Okay, so this is basically the summary of transistors operating in active mode. So you just focus on this column because we will not be covering PNP. So in active mode, your VBE is approximately 0.7 and VCE is greater than 0.3 volt. In saturation mode, VCE, this voltage is going to be approximately 0.2 volt, and VBE is going to be VBE is going to be forward biased, and this part is going to be forward biased. So therefore, IC is going to be less than the IC that we have in active mode. So here in this slide, I have just summarized. Now what I would like you to do, here is also summary of the steps to analyze. So you have applied junction biasing condition, active mode. You have emitter-based junction, forward bias, and collector-based junction. For PNP it is different, but you don't focus on PNP. Emitter-based junction is going to be forward bias. Collector-based junction is going to be reverse bias. I just reiterated, I just summarized in one slide nicely. In saturation mode, both junctions is going to be forward bias, and collector-based voltage is going to be 0.2, which means that almost 0 volt. You apply KVL KCL. We did apply KVL KCL right here, and you can verify the assumption that is the transistor operating in active mode, is the transistor operating in saturation mode. So based on the voltages, collector voltage, base voltage, and emitter voltage, make sure you determine collector voltage, emitter voltage, base voltage, and based on the difference between voltages VBE, VCE, and VCB, based on the differences in these voltages, you will be able to determine whether or not transistor is in active mode, operating in active mode, or in saturation. Whether or not transistor can be used as an amplifier or as a switch. So we have another example. This example, consider the circuit below this. This circuit is even easier. Here you have grounded. So please include this in your scribe. Solution of this example, make sure you include this in your scribing. And yeah, more examples, exercise, and problems. I have listed a few exercises from this chapter, but I am before the exam. Before the exam, I was able to complete this chapter. So in the same PDF document, I am going to upload some more exercise problem, more end of chapter problem for your practice in the final exam, right? And before the final exam, I think we have next week, we have another exam for this course, no? All right, so I will see you on Thursday, guys. Make sure you prepare to run your piece marks. Okay? And also, guys, okay, I still have one more. Okay, make sure you look at the assignment, laboratory assignment, read the laboratory handout. Okay? See what you are supposed to do. At least you should know what you are supposed to do. Okay?